So let's welcome Huaxiu to give a talk here. Thank you.
Okay. Hello everyone. Thanks for the invitation. Well, I'm really happy to give a talk here and to visit Japan. And today my talk is about the alignment in multimodal foundation models. As we can see, the large vision language models or multimodal large multimodal language models that already be used in a lot of places. So what we need to do is just to input like image or kind of videos, and then we have some questions, and then these large language models can integrate this kind of multimodal information and to be tokens and to feed into large language models, and then to produce what you want to do. And so you can do like some mobile manipulation if you have some robot, and you can let the robot do to generate some actions and do manipulation. And you can also do some vision question and answering, captioning, or any kinds of large computation tasks. And you can also do some language only tasks, just ask the large language models and to answer some questions. And also you can do the task and motion planning or like tabletop manipulation. So, and this kind of like large multimodal models already be used in a lot of places like autonomous driving, like the chatbot, and also like some robotics. And so this is very exciting advance. So in using this kind of information to help our daily life. And there are some challenges behind these large vision language models. So basically, these large vision language models are prone to hallucinate and generate non-factual information. So basically, we can see, in the right figure, we have the visual input and have like two images. And if we feed this kind of image into like this large vision language model, this is an old image and maybe from like 2023 or something. And these models are either to produce something wrong. So, which, for example, in the first image, and it states that there are shower in the corner, but we didn't see anything like actually in the corner. These kinds of like large vision language models are very easy to generate some non-factual information. And also another example we can see that these models can answer well if we have like the embedded text as English, but it will perform worse if we see the embedded information would be Chinese. So this kind of informations will also generate some non-factual information and hallucinate. And basically, we will like say that these hallucination issues will be caused by the misalignment or over different kind of modalities. For example, like in this large vision language models, and basically you have the image and you feed it into the projector and combining with the language instructions, and to get some language response. And this language response may not align well with this input image. So which will reflect is that these models sometimes will ignore the image information and only leverage the language spurious correlations and to answer these questions and to get the response. Okay, so there are some kinds of like a misalignment between this output language and the input images. Okay, to address these issues, there are a couple of ways. Basically, we would like to say these large vision language models cannot solve the problems by themselves. So we hope to leverage external knowledge. And this external knowledge is that we can leverage the knowledge retrieval. And if there are some like database, and this database can provide the useful information or helpful information to solve this problem. And basically, we will feed this text and image, feed these multimodal informations and to the knowledge base. And in this situation, this knowledge base will provide sufficient information and to guide this generation. So we do the retrieval augmented generation. And in some situations, and here I put one example we do on like the medical imaging analysis. So in some situations, by doing this way, we use the retrieval knowledge can significantly improve the performance and to reduce the hallucination. And that means that this kind of RAG information would be very useful. But if we highly rely on the knowledge retrieval, this is not enough. So basically, if, for example, like this in this medical imaging understanding, so we have the medical image, and we also have its corresponding reference. But this corresponding reference may not be that reliable. Okay, so if this reference is not reliable, specified for this like medical imaging, and if we purely rely on the knowledge retrieval, this way make these models to answer incorrectly. So even in some situations, this model can answer it well, but after introducing some like references, and this reference contains a lot of irrelevant or even incorrect information, and they will also cause like these models to answer wrong. And so basically, we would like to say that this unreliable reference cannot help or even hurt the performance. So to further leverage both things, the overview of today's talk is that I will first discuss some of our recent methods to enhance alignment in large vision language models directly, and we will also discuss how to enhance alignment in some complex retrieval augmented generation. Okay, I will first start to do something to directly enhance alignment in the large vision language models. To improve the alignment of these large vision language models, and the basic method is we can directly to fine-tune these models and to make it align well with the preference, with human preference. There are two ways to do that. The first way is that we can construct some data set and to employ the supervised fine-tuning. So there are some high-quality data sets that can curated by human responses, and then we will leverage this kind of like a supervised fine-tuned data set to directly fine-tune the standard language modeling objective. So we probably will use some traditional losses like autoregressive loss to fine-tune these models. Another way is that we can leverage the reinforcement learning to do something like that after doing the supervised fine-tuning to achieve the better alignment. So here, to apply this kind of like a reinforcement learning, we will first curate some preference data set, which preference data set can be annotated either by humans or can use some advanced language models to annotate this preference data set. Like here, we have the preference pairs, and we can build some reward models, and these reward models can help us to train these large language models by using some like reinforcement learning. Okay, so this is the ways that we would like to specifically focus on to use a kind of like a RLHF or RLAIF to fine-tune the models and to let these models to be well aligned with the human preference. Okay, so to achieve this goal, the most important thing is how can we curate the preference data. So basically, like this kind of RLHF just use some like very simple reinforcement based algorithms, but it have like a very high requirements of the data set we want to curate. So in the 2023, that is the OpenAI used like this kind of human preference and to curate a lot of human preference and to have the human labeler to rank this like output of every prompt questions and to get like this ranking of these generated responses. And but in this situation, if we highly rely on the human data labelers, so this data curation and annotation process would be quite expensive. So one way to address these issues is that we can fully leverage the supervised fine-tuning data. So basically, the supervised fine-tuning data is usually associated with some high-quality data. And this modality misalignment will be widely exist in the supervised fine-tuned large vision language models. So if we can leverage the supervised fine-tuned data, and we can significantly reduce like the cost to use human labels. Okay, so basically, like the supervised fine-tuned data can be formulated as the XY pairs, and the label Y in this SFT data can be regarded as the natural preference response. So we will treat it as the preferred data with the ground truth labels of the supervised fine-tuned data. So what we want to do if we can fully leverage the supervised fine-tuned data is that we need to generate some like this preferred data. So it means that we have the ground truth and we want to hallucinate the ground truth and to get some like this preferred information. Okay, in our pre-work, so in 2024, in early 2024, so we built some works to leverage some strategies and to generate this kind of this preferred data to fine-tune the models. And basically, we can leverage the prompt to generate some hallucinatory response. So we will let the GPT models and to inject some like hallucinatory information into like this preferred response. So one way to do so is that we can have some co-occurrence. So you mean, for example, like the chair and the tables always happen together, but in some new image, and this will cause some spurious correlations, and these models will rely on this information. So if it produce the chairs, it will also highly likely to produce tables. But if in the testing image, so they didn't have these kind of correlations, and we hope like these models can distinguish the preferred response of this preferred response, where the this preferred response will rely on some like spurious correlation to do something like that. And we can also inject some information and to curate the preferred response. And another way to do that, so is that we can also like to distort the image to trigger some inherent hallucinatory patterns. Basically, we can see there are one questions to describe the image, and we actually there are a fork a plate here, and if we add some noise, and when we add some noise, slightly add some noise, when we have the noise steps at 500, and we can see there are these models will become fork and will produce fork information, but this is wrong. But this is that these models, all humans can still see this image well, but these models will produce some hallucinatory response. Okay, and if we add a lot with a noise, these models will be pixel. But we can see in the right figure, it depends on the noise steps, and these models can produce some like a reasonable or plausible information, but it's wrong. So this is what we tried in our early stage, and to curate some like this preferred data based on the supervised fine-tuning data, and to perform the preference fine-tuning and to improve the model's alignment.
I have a question here. Okay. So the traditional pipeline of the fine-tuning is first we supervise the fine-tuning and then alignment. So in your pipeline, you still have the first stage of supervised fine-tuning and reuse the data of the supervised data to enhance the preference data set and do the IRHF in the second step. Is that right?
So basically we just use supervised fine-tuning data and treat it as preferred or like as a positive data.
Okay, and so you do not have additional data sets like the preference data set?
Yes.
Okay, so is that somehow like the overfits? Is that will overfit the data sets of the supervised fine-tuning?
Basically you can see that if we want to have the new data set, we have so many supervised fine-tuning data. So it depends on how you inject these hallucinations. Yeah, because if you use supervised fine-tuning and you continuously use supervised fine-tuning, you will also overfit.
Oh, okay. Okay.
Yeah.
It's related. So basically, if you construct the preference data in this way, so why it can be better than SFT? An information theoretical point of view, because you basically you don't have new information. That's also a critic against the DPO versus IRHF, because IRHF you may have new information, but in DPO, basically the information is fixed. But the data set, the training data set for DPO is different from the training data set of SFT. But then here, if you construct the preference data, the parent data from the point-based supervision, why it can be better?
But the injected information will inject some like new information from like the either GPT or something.
No, I mean in descriptive learning, this will not work. If it's this descriptive learning, like for example, contrastive learning, if the positive data is fixed and you repeatedly sample different negative data, it will not really improve the performance a lot.
So you mean like things like this data didn't provide additional information?
Not only that, because okay, maybe the question is long, but because you don't really try to employ, you just exploit the current data you have, then I think because you are doing the preference alignment maybe by RHF for example, then it's similar to imitation learning versus deep reinforcement learning. If you rely only on imitation learning, you can start up very quickly, but the final performance cannot exceed the human expert who provide the demonstration.
Yeah, I understand. Yeah, I understand. Yeah.
But if you first do imitation learning and then reinforcement learning, then the performance of the agent can be better than the human expert, especially when the human expert cannot provide a perfect or optimal demonstration. Here, I assume that the question may be, the task may be very difficult. So even the human expert who provided the Y part for SFT may not be optimal.
Yeah,
It's
yeah.
very good, it's very high quality, but it's still suboptimal. So in that case, if you really construct the preference data from the supervised data,
So you mean there are some like bottlenecks for this performance?
yeah, the ceiling glass. Maybe currently the model does not really exceed the ceiling glass, but later.
Yeah, but this is also like some questions like the current large language model faces. So you know, like the language when we do like some I collaborate with some people in MBCUI, so they curate a very large data set. And if you can still doing some subsamples from this data set already actually it's already used the kinds of like all the informations,
Yeah.
you know, like from the internet. So if you can only leverage this information to further improve it. Yes, this is like also some questions that happens in a lot of like language model trainings.
Yeah, because I'm thinking about unless it's like some math Olympic or something similar.
Yeah.
Otherwise, the optimal response may not be unique, especially something related to social science or economics. The optimal response may not be unique. If we say for this question X, the answer should be Y, then maybe the model will not explore other alternative equally good answer.
Yeah. So basically, one solution is that you can also let the models to like let the models itself to exploit and to generate something like that, and then to use kind of like reinforcement or something like the techniques that are right now used. So to directly optimize it for some open question.
Okay, but as he asked, currently you don't have additional data set.
Yeah.
Okay, but still the performance get much better.
Yeah.
Okay.
Any other questions? So I think I can continue.
Yeah, please.
Yeah, okay. So so basically this is the first thing I would like to briefly discuss about if we in case that we have some isolate data, but what if we do not have a lot of like supervised fine-tuning data and we see can we like directly generate the preference from the model itself? So basically we can do like kind of like a self-rewarding doing something like that. So you have the language models and you can generate you have a lot of like a new prompt and you will like this model to generate a lot of responses and let the models to generate a reward for that. We use some same model. And then you have the preference pairs. You can do like kinds of like preference optimization and based on these preference pairs and to get like the enhanced models. But if we directly apply this to the vision language models, and this vision language model also will like to amplify this bias if we use simple models to do the model to the response generation and do the to do the rewarding. And so this can also like a modality element happens in both generator and the judge. And so our goal is like we would like to say that this generator preference may be potentially biased. Okay, so whether we would like to see whether we can calibrate it. And so we propose like the calibrated self-rewarding to do something like that. So basically, this is like we hope to iteratively self-improve the performance and every iterations and target vision language models can generate the preference data and perform the preference optimization. And we will use like the self-generated preference to guide and by the reward score by itself and to calibrate by some image response relevance. So basically, this method performs very well over like different, maybe like 10 benchmarks. And we can also see like these models can achieve the self-improvement performance on the models in the level of 1.57 billions. Okay, so the key steps of the calibrate reward models, a self-rewarding method is to do the first we do the reward modeling. And here we will do the step-by-step reward modeling and to enhance the fine-grained rewarding. And the first thing we have is like the users will have the prompt, and we will let the prompt to feed into the large vision language models. And basically, you will have a lot of like you can generate a lot of sentences first. The first sentences or first paragraph will represent partially generations of these large vision language models, and then you will have like something like a self-rewarding or calibrate self-rewarding mechanism, and to rank these generated groups Okay, here we will also like to leverage the image and text information to calibrate it. So we have you have the search space and you have different kind of options. And then we would like to rank like these different kind of options and to select the most reasonable, the most high score ones and the low score ones. And then we would like to leverage the selected ones to generate the second sentences group. And then you will rank it, and you will iteratively generate and rank it by every steps. So here you will like to do first doing the step-by-step reward modeling. And then we will like to do the calibrated self-rewarding. And basically you will like the models to reward it by itself and to use the RT here. And the RT here represents language sampling probability, and the higher probability we will treat it as high reward, and to rank like these sentences. And we will also like to leverage the image and to provide additional calibrations on this like the pure language rewarding. And here we would like to use some like image relevance or response relevance score, which is calculated by some clip models, but you can also replace it to some additional models. And we would like to get these combinations of this like image rewarding and the text rewarding, and to finally to get the reward of these kind of models. Okay, so you will have like this calibrated reward, and then to rank these sentences and generate by the image, by the models itself. And finally, we will also like to perform this kinds of like a self-rewarding for multiple times. So you will first have like these generated sentence groups, and also have the preference data, and then you will like to generate the performance preference optimization and get a stronger vision language models or large vision language models, and then you would like to leverage the stronger models to generate the responses again, and then rank it by using some rewarding methods. And finally, you will have the new preference data, and this new preference data will like to trigger to the stronger models, and then you will like to do the self-improvements. Okay, basically we the overall performance CSR, the calibrated self-rewarding, requires only the image data and the large vision language models and the clip model, and it can achieve this self-improvements using these models, particularly when compared with the traditional self-rewarding paradigm. And basically, we can see these models can improve the performance over the compared with the original models and compared with the self-rewarding approach.
What LVRM do you use?
We use the Labas 1.57 billion and the 1.513 billion as the base models for that.
Is this strong enough?
At that time, it's enough, but right now, I think it's not strong enough. So it moves very fast.
Okay.
Yeah. In the 2024, this is works happens in early 2024.
Right.
Yeah.
In your previous slide, you have VLLM. I guess it's same as LVRM.
Oh yeah, yes. This is a typo, I think.
Okay.
So sorry. Yeah. Okay. So, and then we also evaluate the self-improvements things, and to see that whether these models can iteratively optimize and to continuously enhance the performance across the iterations. And we can see like across different iterations, these models can improve the performance over different iterations, and starting from the base models, and the largest improvements will happen in the first iterations, and then it will be like becomes converge. So this is also very common. So this is, but it's also introduce some like open challenges, and this kind of like a self-improvement models are very easy to converge. So this kind of converge things will also like to be as kind of like associated to the, some overfitting issues. So this would be one open questions for future explorations. And we also to analyze some like the change of like image relevance scores by applying the calibrated self-rewarding methods, and we can see two kinds of things. The first thing is like vision language models will become closely aligned with the image information. So we visualize the base model, and which is like the base model with rejected response, and chosen response is like preferred and dispreferred responses. And we also visualize calibrate self-rewarding of our methods, and with the rejected response and the chosen response. Yes, and we can see like the image relevance response relevance scores increase. So it means that these models becomes more closely aligned with like the image information. And we also like to compare with the original models. We compare the gap between the chosen response and the rejected response. And our methods, after applying our methods using the rejected response and chosen response. And we found like the gap after applying our method is much smaller compared with the original methods. So this makes like these models more harder to distinguish between this self-generated preference data over different iterations, which becomes more and more challenging after applying our method. So it makes these models can self-generate a lot of very similar responses and make it harder to distinguish. But for the original models, this is much easier to distinguish. So it means that the original models still have a lot of rooms to get the better alignment. And we also visualize the compatibility of these models by applying to we see the Llama 1.47 billion, also like the Villa 7 billion. So this is some models happens in early 2024. And finally, we also visualize some like visual tokens of that. And these visual tokens, we can see after applying this kind of models will enhance like the attention values of these visual tokens. And for some like case examples. Okay, so we provide some very simple theoretical analysis and with like image relevance calibrations. And this kind of models can increase attention to the image will further improve the performance. Okay, so this is something that if we do not have the supervised fine-tuning data, we can use these models to generate the data samples and then to rank it and then to finally achieve better performance. So later, we also further release the constraint of this self-rewarding to release this image relevance evaluation with some external models to do this kind of rewarding. So we provide a general framework of agentic framework for the preference data synthesis. And these kind of models will introduce a collaborative two players between the target model and the judge models, which will be assisted by some external tools. And I will go to the further pipeline step by step. And basically, in the first step, so we will have the data sources, and these data sources we can leverage a lot of different kinds of tasks. We can do the natural language tasks, do the natural image tasks, also medical image tasks, and some like visual language action tasks. And then we will leverage the target model to generate the response. And after this target model generated the response, we will like to use the judge models to judge like these average responses. And these judge models to achieve like the better judgment. So we will improve it by leveraging some external tools. And these external tools could be treated as like different tool card. And like the web search, we can do the ground SAM, and we can also do like some uplift tool of these kind of models and to better enhance like the judge models and to provide additional knowledge like the bounding box, like the labels, like the short captions, and to enhance these judge models and to get the better judgment. So the second step is to judge the model and to give us score. And after we get a lot of the candidate responses and to rank them, and we will feed it into a reward model and to get the reward. So the ideal reward model is just we need to evaluate the generated data quality, and these reward models need to make it as like a target model because we can use generated responses and to train the target model. And then we can use this performance of this trained target model and to see whether this is performance well or not, performance better or not, to judge the reward. But it's very hard to evaluate. So it's so costly. So we use like a proxy reward models to judge and just to prompt these reward models and to justify whether some response is better and whether this like the rewarding and these like rankings would be better or not. So if it is good and pass the criteria that provided to the reward models, and we will present these generated responses and to the preference data set to construct the preference data set. And if not, and we will like to leverage the feedbacks from this reward model that this is not past the reward models and to do the prompt optimization of the target model and judge models and to optimize the target model and judge model, because if you change the prompt, you can treat it as an updated model for this target model and judge models to first generate this kind of like responses and also to judge whether this response would be make sense or not, would be precise or not, and to improve the rewarding and to get the better ranked response. Okay, so after we doing that and we evaluate these kind of models, on different tasks. We can apply it to the natural language generation, and we apply to 5 data sets. We also do the natural vision language understanding, and to apply some tasks here. We will also like to do the medical imaging analysis and to see that whether these models can generate a medical report, correct medical report, or like to answer correctly all the medical questions. And we also put some visual control, some vision language action tasks, and to compare with the performance of the target model only, or like doing self-rewarding, also like some the meta rewarding, which is also some kind of methods that proposed by the same team of the self-rewarding, and to see whether our method can further improve the performance. And we also compare the performance on this natural language generation, natural language vision understanding, medical imaging analysis, and the visual motor control to see that whether these kind of models could get the self-improvements over different kinds of iterations. So after we generate once, and we fine-tune the model, and the model will enhance, and then we generate the new data, and then we use the new data to fine-tune the model and get the model to see that whether this model can do the self-improve. And we also like to show some like correlations between this like the reward score and the preference. And we can see over different kind of iterations, and the average reward score will increase. So it means that these models will further like to get the higher reward scores after training these models over these different iterations, and with the same prompt to judge like the generated response. And there are also like some correlations as a positive correlation of the reward model and the reward score, and the performance. So it means that the high reward score is associated with the high performance. So in this situation, it means that this like a reward score can reflect the human performance, and this like we can use kind of like a surrogate reward models and to provide the reward and to justify the responses generated by the model. Okay, later we also show some application studies, and here we do the 2 application studies. One is to use the total augmented judgment, and also like some feedback mechanism, and to apply to different kinds of like downstream approaches. So we can see that this is like a tool-based augmentation can improve the performance, as well as we use the feedback mechanism to optimize or to do the prompt optimization on these target models, and the judge models can further improve the performance. Okay, this is some analysis that we did on these tasks. Okay, we discussed some methods and to say that how to leverage like the preference data generation or preference fine-tuning and to improve the alignments of the large vision language models. And we will also like discuss a little bit about our use case, that very interesting use case that we use, we apply such kind of methods to some like downstream applications to do the robot control. And we would like to see that whether this alignment can also help in these vision language action models. So previously we did a lot on this like vision language question and answering to the captioning and do these like traditional computation tasks. And we will also see whether this kind of like the alignment can help in this like manipulation. So here we would like to use some models and to use vision language action models. And these vision language action models will produce these actions if we prompt this kind of like the robot arms, say that you would like to grasp one apple, for example. And then these models will produce the actions and to guide this like these robot arms and to pick these apples. Okay, so for this use case, we do the vision language action alignment in robotics. So basically, we hope to generalize these vision language action models doing this trajectory-wise preference alignment and towards some like customized objectives. And basically, the first step is to do the trajectory preference optimization. So we have some user instructions, and this user instructions, for example, is to pick up the grape and put it into the pot. And so we have the training task, we have the original image, and we will feed this kind of like a couple of images into these supervised fine-tuning based vision language action models and do this online sampling. And we can sample a lot of trajectories. And based on these trajectories, we will like to have some alignment objective, and this alignment objective can customized depending on the user's preference. And then we can get the preference ranking to fine-tune these like the vision language action models. And we will like hope to do some like trajectory-wise preference optimization. Basically, compared with the stepwise fine-tuning or like stepwise preference optimization, so we here hope to leverage the whole trajectories and to get the trajectory-wise preference fine-tuning. So basically, we would like to integrate different kinds of steps and to leverage that whole different kinds of steps and to fine-tune the models. Here, the key point is how to define these alignment objectives. And so we hope to design some like customized alignment objective. So we feed the initial state and the task instructions to some like visual language models. We use like GPT-4 to do something like that. We have the customized alignment goals to have the task completion, for example, the safety, the efficiency, and these kind of things. We have some customized alignment goals depending on the user preference. And we will let the visual language models to get or like to code some kinds of like functions. And basically you have some key point, and then you will leverage this kind of key point to based on the defined cost functions that is generated by the GPT and to customize or to calculate this kind of reward depending on the scores that the GPT guide you to have like this kind of different stage. So we will first split to the different stage, and every stage you will have its own scores, and finally you will have some combination of these different as scores from different stages. So we can see the stage 1 here, for example, is pick up the grape, and stage 2 will be moved to the pot, and stage 3 will be dropping into the box. Okay, so you have like this kind of stage-wise reward model calculations for this cost function. And then we will also to see something like an iterative alignment to further improve the performance. And we evaluate this kind of models firstly on some like simulations environments. And in these simulation environments, and we do it on the simple environments. And we have the in-domain generation. So we choose the in-domain generation, and we also change the subjects, and also like to move some semantics and depending on the language prompt. And we do 3 types of the auto distribution generation. The first one is subject generation, physical generation, and the semantic generation. And we can see compared with some state-of-art models at that time, so like the Octo and also like the OpenVLA supervised fine-tuning, and also like we apply the OpenVLA DPO on it, and our models can perform better compared with them. And we also like to apply to another environments, to the liberal environments. And we also perform like 4 tasks: the liberal spatial, the liberal objects, the liberal goal, and the liberal run. And we also show the improvements of our method compared with the previous baselines. Later we do some like some pick and place tasks in the real world robots. We have like the in-domain generation. We perform, I think, around like 100 tasks, or 50 to 100 tasks, and we will summarize it to 6 categories: the in-domain generation, and also like to visual generation, and to change like the shapes or like to the objects. And we also have the subject generation, and to see previously we will pick up the banana, we will also change it to pick up the trips. And also like some action generations to fold the green towers from the right to left. And we have the semantic generation and the language grounding. And finally, we get the average performance compared with some baselines using the Octo or OpenVLA SFT or OpenVLA DPO. So this is a like kind of generation performance across different environments. We will also like to show some performance of the customized alignment objectives. So, and to see the first alignment goal is to maximize the task completion. And after the alignment, and we can see these models can perform well on these kind of tasks. And we also illustrate the safety issues in this alignment goal. So basically, before the alignment, and these models are either to have some collisions before the alignment. So after the alignment, and we can see this model is more smoothly grabs the things and to pick the to drop into the ball. And we further compare the cost efficiency when we treat like the cost efficiency would be the major goal of the customized alignment. And before that, we also show the performance before the alignment and after alignment, and to see like whether these models can more quickly or more efficiently to achieve this goal. So this is like a kind of like user case if we hope to apply this like alignment to generate the preference data and into the robotics. Okay, so this is the first thing I would like to discuss today and to enhance alignment in the large vision language models. And we also have some students doing some like works to enhance the alignment in the retrieval augmented large vision language models. And there are two types of the misalignment when we use like the tools or RAG. So basically, I will choose them as completely the same things. So you can leverage the external knowledge and to guide these models and to enhance these models. And the first alignment in this like the when we use large vision language models with tools or RAG is that the cross-modality alignment is basically these models may disregard the image modalities just relying on the text. So even the image holds some critical informations. And this is like cross-modality misalignment. This is what we discussed a lot before. And another alignment is that this model ground truth trust misalignment. So basically the retrieved information may interfere with the model's reasoning process, so which will finally lead to some hallucinated or like incorrect outputs. So basically it means that you will have some additional information captured from the external database, but this kind of additional information may not make sense. And even some like incorrect information or irrelevant information. And this irrelevant information or incorrect information may interfere with the model's reasoning process. So to address these issues, we propose a framework to address this alignment challenge in the multimodal RAG systems. And we also provide some additional use cases by leveraging this process. So we can treat this problem as that how to solve this problem is that the first thing is that we can see like when we model need to solve the problems. So it will directly leverage the generated or the retrieved information to generate its output. So basically we can do some simple things like that. We have the ground truth. And the ground truth is that this model, when we feed the original image into these models, and these models will produce correct information. But if we feed into an unrelated image, and this unrelated image could be purely noisy image, and to feed this model, and these models will know this is not like the correct. But if we introduce some like retrieved information or tool captured informations, and these models will have the original image with this retrieved knowledge, and these models could answer correctly. Or this is what we expect to see. And what we do not expect to see is that we will have some unrelated image. And this unrelated image with the same retrieved informations and feed into the large vision language models. And these models can still generate the correct response. So what does this mean? So it means that these models, you will purely ignore this input image and only leverage the retrieved information to make the generation. So it means that it's just a copy what we retrieve and to get the response. And this is what we do not want to see. So we will treat the first cases, you feed the original image with the retrieved knowledge to the large vision language model as a positive example, and with the unrelated image feed into the large vision language models as a negative example. And then another situation is that you cannot solve the problems by this model itself. So they will like to leverage the knowledge retriever to improve the performance. So it means that when you feed this original image into these large vision language models, and these large vision language models can generate the correct response. And if you feed without this retrieval knowledge, these models may generate incorrect information. So it means that this is what the original motivation of the RAG. So it means that the model cannot solve it, and then with the RAG, you can solve it. Okay, the third situation is that we are thinking of one scenario is that we have the copied results, so we have the RAG information. But the RAG information even interfere with the model's decision. So basically, we can think one scenario is that we feed the original image into the models, and this model itself can solve the problems. But with RAG, so this RAG information may maybe incorrect, maybe irrelevant. So maybe provide a lot of information. And when we have the original image and feed it into the RAG and feed it into the large vision language models, this will even generate the incorrect response. This is not we expect to see. Okay. So based on these scenarios, we will like get a mixture preference data and then to performance preference fine tuning and to improve the performance. And this kind of like framework would be easy to use with slightly tweak on some like downstream applications. We specifically do some like 2 applications. And the first use case is about the multimodal medical RAG. So this is a collaboration with some like medical doctors, also like some medical expertise, and to develop the medical multimodal RAG. So basically, we hope to build like a unified multimodal RAG is that we will do the multimodal medical retrieval. So we have different kinds of data, and this data made from the radiology, from the pathology, and we have the domain identification and to determine the corresponding imaging domains for this like a radiology or pathology data. And we will have the will be feeding into the corresponding retriever, and this retriever could be the pathology retriever or the radiology retriever, or like more. We have the multiple domains. And this kind of retrieval process is basically, so this is also one typos, and the red is not here, so we captured from some other papers. And basically you will have the target image, and you feed into some fine-tuned clip models and leverage the clip models and to find some most similar medical responses from this database. And we will leverage this retrieved medical responses combining with the original image and to feed these medical large vision language models and to generate the response. Okay, so because like not all retrieval information would be useful before applying what we discussed before to leverage the RAG-based preference fine-tuning, and we will also do some additional things to first filter out some irrelevant like retrieved information. So we do some basic analysis and to see that where we retrieve the top K reports, and based on the trend increase of K, we can see the validation accuracy will first increase and decrease. And also like the test accuracy will also increase and decrease. And basically on this like clip scores of the target image relationship with the retrieved informations. And this will decrease definitely. So based on like the top K reports we would like to retrieve. So we apply very simple ways to do something like that. Like we do some adaptive retrieve context selection. So we have the medical imaging and we have the domain labels, and we feed into the corresponding retriever, and we get the top K reports, and we leverage some like similarity scores. We also leverage some like a simple like predictions to estimate the uncertainties for this kind of or relationships for this kind of top K reports, and then we will get these adaptive K reports for every medical image and to feed into the medical large vision language models. After that, we will leverage the preference fine-tuning or like the RAG-based preference fine-tuning and to see that whether these models can generate the correct responses. Okay, so we apply this kind of models to the LlamaMed, and the first line is the original models, LlamaMed, as the LlamaMed 1.5, and also like some ways to reduce the hallucinations for this LlamaMed 1.5, also some several retrieval-based methods. And we can also see the improvements of the MMed RAG. So Louis, our previous works in EMOHI 2024. So we also see as improvements of MMed RAG. And we also generate some like reports and to use the MMed RAGs and to comparing with the LlamaMed 1.5, we can also see like the improvements of using the MMed RAG compared with the original models LlamaMed 1.5. Later, we do some like simple analysis and to see how this kind of like RAG-based preference optimization can help the performance and to reduce the misalignment issues that we discussed before. So the first experiments we hope to do is about we define 2 kinds of rates. The first one is about the over-reliance rate. The over-reliance rate means that the original models can answer correctly, but with RAG, it performs worse. It performs bad. It generates an incorrect response. So we calculate this over-reliance rate and the baseline would be more than 40% over reliance rate. But after applying our methods, we can significantly reduce the over reliance rate to less than 10%. And we also define another rate would be a copy relevance rate. And here is that we see that some models directly copy the relevance information without considering the image. This is what we discussed before, is that these models discard this kind of like image information and only relies on the retrieval knowledge to make the prediction. Okay, so in this rate, so the baseline would be more than 50%. So even we feed some like a purely unrelated like a noised image into the models, and these models will still produce the correct information with RAG. So, but after applying our approach, we can reduce it to less than 30%. Okay, so we also do some like a basically analysis and to show the relationship between the image tokens and text tokens. So this is the first use case is we do some like a multimodal RAG. And another use case is that we collaborate with Adobe and to do some like a document understanding, which is an important application in their like scenarios. So we propose a multi-agent systems and to do the document understanding. So we have the original system, and this MDoc agent is like a multimodal multi-agent framework to do the document understanding. And different agents, there are multiple agents, and different agents can collaborate to answer queries based on some complex multimodal documents. So the framework details will have like a multiple stage. And then in the first stage, we will like to leverage some PDF tools and to calculate, to capture the pure text information, or this like the image information of like this long document. And then we hope to leverage this kind of information and to feed into the text-based RAG and the image-based RAG to get the top K segments of text and to get the top K segments of image. And then we will go to our like a multi-agent systems. So the first things is that they have a general agent, and this general agent can handle the multimodal reasoning process, and we will prompt it to do the multimodal reasoning process. And then we will like have the critical agent, and this critical agent will to analyze what's generated from this general agent, and to refine the answers by identifying some relevant context. And then we deployed a text agent and the image agent, which is focused on the text-based content and specialized in the vision content. So we have some like critical text information, which is analyzed by the critical agent. And it means that there are some information that is still missing, and take more look on the original documents. And the text image agent will analyze the text information and to generate the answers from text. And the image agent will generate the answers from the image, also analyze the critical visual information that is captured by the critical agent. And we will leverage the original answers from the general agent, the text agent, with some like additional focus that of the critical text information, and also the image answers with the critical visual information, and to have the summarized agent. And this summarizing agent will analyze this information and to answer the questions. Okay. Okay. So, and we will also like to apply the we discussed the RAG-based preference data curation pipelines into the models, and to preserving this alignment across the multi-agent systems, and to curate some preference pairs for the text agent, for the image agent, and also like for this general agent and for the critical agent. And this is not that complex, although like the figures looks a bit complex, but the Q process is not that complex, and we just based on the applying our like RAG-based systems, preference fine-tuning systems into these models, and to do something like that. And we apply to 5 data sets with the document understanding, and to see that whether our models can achieve the better performance, and also like with the alignment or with the RAG-based preference fine-tuning can improve the performance. We calculate the average on these situations, or compared with some baselines. Okay. So this is the last part. We discussed some how to enhance the alignment and how to curate the high quality preference data with the knowledge retriever, and to augment the large vision language models. So this is the second part I would like to discuss for today. And this is actually all I would like to share for today's talk. So, okay, thanks. Any questions?
Any questions? And also, if you have any questions, just write down in the chat room in the Zoom, in Zoom. Okay, I have one very quick questions.
Okay.
So in the robotic parks, I think you are using the DPO, using the trajectory preference data. Is there any theoretical guarantee for that?
No, at that time we didn't do any like theoretical guarantees.
Yeah, I see.
Yeah, but just like to capture the relationships of the whole trajectory to provide the reward. Not like
Okay, so
based
you
on
are
single step.
considering the trajectory as one sample.
Yes, as one sample. So
Oh.
although like these models is produced one steps at that time. So right now they have some advanced models and we are still improve our frameworks. And but at that time, so these models just generate the next steps, and then you capture new image and feed the models again, and the models will generate the new actions, and then you capture the new image and then feed the model again and again. So at that time, so but we hope to leverage this whole trajectories compared with just using stepwise preference optimization.
Okay, I see. Okay, thank you. Any other question? Yes, due to the time limit, we just finished the talk here. And if you have any further questions, please just contact the speakers. Okay, thank you for attending.